Something is coming.
Something big. Here in the Pacific Northwest, we're due for the Cascadia megathrust earthquake. And with an earthquake this massive, even areas hundreds of miles away will feel its devastating effects. But what if we could reduce the amount of devastation the earthquake causes? Actually make areas of the ground immune to the worst effects of the shaking. It could save buildings, infrastructure, and even lives. And that's all science, no fiction. It's not easy to know what's going on in the ground beneath your feet, but that's what it takes to understand what'll happen during an earthquake. Portland State University researcher Fadzai Zvanai is testing out a new soil treatment that could reduce the damage caused by earthquakes. It takes a high-tech hammer.
The connection is so finicky.
And some very low-tech pipes to measure how quickly sound waves travel through the soil.
There's waves.
The speed will show how saturated the ground is with water, which is a sign of how likely this soil is to turn into a soupy, sloppy, liquid mess during a major earthquake.
You're good.
Oh my goodness, I think about Cascadia and earthquake shaking or the earthquake risk here quite often. Here in Portland, we have a lot of structures that were built before we had a real understanding of the seismic risk in the area.
Cascadia, the big one. Predicted magnitude 9. It's not if it will happen, it's when. Cascadia will send massive shockwaves through the earth, like the sound waves on these drums. The resulting damage will be widespread, like it was in Alaska in 1964.
This is what happened in downtown Anchorage.
And one of the most devastating side effects of a large earthquake is soil liquefaction.
The geologists found that earthquake vibrations themselves caused less heavy damage than the vibration-induced sliding and settling of weak deposits beneath the city.
Liquefaction happens when vibrations from an earthquake hit soil that's fully saturated with water. Normally, when shaken, the particles of soil want to settle, like these beans do when you tap the side. But saturated soil can't compress because there's water in the way. The intense downward pressure causes the water to squeeze in and fully surround the particles, which makes the previously solid ground flow like a liquid. Buildings sink or tilt. Pipelines pop to the surface. Unsecured bridges destabilize. The longer and stronger an earthquake is, the more likely liquefaction will happen.
The idea is that for the soils to liquefy, you need to have 100% saturation. Not 99%, but it has to be 100% saturation. This method works by reducing that saturation ratio from 100% down to whatever level required for it not to be liquefiable.
Hosra Vifar and his team are trying to desaturate the ground using some unlikely allies, the hungry microbes that naturally live in the soil.
So this is the garden soil. So this is called calcium acetate. Then you also mix, this is called calcium nitrate.
The two ingredients together are a microbial smorgasbord, When you pump the nutrients down into the ground, the microbes in the soil feast.
Basically, these microbes are eating the nutrients and producing nitrogen. And this is what you want to do happen underground.
Exactly. The microbes which already exist in the soil will be stimulated by that nitrate solution. So when they get stimulated, they will produce nitrogen gas.
That nitrogen pushes some of the water out from between the grains of soil, effectively desaturating the ground.
So when you think about those microbes and what they're doing, are they burping or are they farting?
I think they're doing both burping and farting. Yeah.
Whatever the microbes are doing, Svanai hopes to simulate it in the controlled conditions of the lab.
So this is what I call the magic tent, where all the chemistry and all the reactions are happening.
She'll run her microbe and nutrient solution, dyed a brilliant blue, through this tank to see how it spreads through different soil types and how long the nitrogen hangs around.
This is the sand layer, and this brown one is a silt layer. And this silt layer is the one which is most common here in Oregon, Portland. And these all soils are liquefiable.
Liquefiable sand and silt soils are most often found along rivers and waterways, where the water table is high. Problem is, this also happens to be where most of our towns and cities are built. In Oregon, there's spots of high risk on the coast, in river valleys, in the mountains, and beyond.
The areas with significant liquefaction are areas of reclaimed land or areas where there's fill.
This is exactly what the ground is under Portland's critical energy infrastructure hub, the tank farms. The hub is where 90% of Oregon's total fuel supply is stored and handled. Much of this industrial area where the tank farms are used to be a lake before it was filled in. The liquefaction risk here is very high.
These are fuel tanks that were largely built before we had this understanding of the seismic hazard in the area.
The state is taking steps to bring the tanks up to seismic standards, but if an earthquake hits before that's done, emergency officials are expecting chemical leaks, fires, and a devastating disruption of fuel supplies when we need it most. Out at the lab's field site near the Portland airport, the team tested their liquefaction fix under real conditions.
So this is a PVC pipe. It's slotted from 5 feet down to 20 feet.
The nutrient solution gets pumped down through the pipe. To make it work underneath a building, you could install a nutrient well on one side and then sink an extraction well on the other. Drawing water out of the extraction well creates an underground flow that pulls the nutrients in that direction. The microbes living in the ground chow down on the nutrients and produce tiny nitrogen bubbles that push out the water. In other words, it desaturates the soil.
Hey, what's all this yellow goo?
All this yellow cake that you see here is the biomass that is created as a result of calcium acetate and calcium nitrate being consumed by the microbes in the soil.
This is like the waste product of all the bacteria?
Yeah.
But it's not toxic or anything like that?
No.
No, okay. I hope not. 'Cause
I mean, you don't want to.
I know.
You don't want to grab a spoon and eat it, but it's.
Well, I won't do that,
Right.
but I did just stick my finger in it.
The field tests, which began in 2019, have shown real promise. All those burping microbes reduce the soil saturation considerably, below 95%. That should be enough to stop liquefaction.
They dropped down and they stayed down for like 5 years.
They successfully retreated the site in 2025.
How far is this technology out from being real-world applicable?
I don't have the answer to that.
Yeah.
That's because there's still many research questions to answer and regulatory hurdles as well. The Pacific Northwest hasn't had a major earthquake in more than 300 years, and we're not prepared for the next one.
This method, if it works, with a big if, but if it does work, then it would have a real impact.
So when it comes to safeguarding our communities from Cascadia, innovative solutions are going to be needed.
Will you say right now on camera that you were single-handedly going to save us from Cascadia?
I'll try my best.
And try to chaos together.
OPB members are like those burping microbes. Y'all keep all science no fiction standing on solid ground. We're here because of your direct financial support. Thanks. And don't miss out on any of Oregon Public Broadcasting's science, environment, and arts programs by subscribing to our OPB Insider newsletter at opb.org/allscience.
Oh my God, the dust.
It's supposed to be low dust.